Hi, welcome. Welcome to our talk. First of all, I hope you had a good KubeCon. I hope you made a couple new friends. If, in case you haven't, please meet us after the talk. We'd love to be your friend. So welcome to our talk, CafeGPT. My name is Madhav. I'm a grad student at UIUC, and I do research in the area of distributed systems. And I also contribute and maintain some parts of the Kubernetes project.
Hi, my name is Kartik. I'm also a grad student at University of Illinois, where I research ML systems. And really excited to be here and see all of you today.
So before we get into it, we'd like to start by talking about what this talk isn't, right? This isn't a deep dive into LLM inference or the internals of how Kubernetes enables serving such workloads. There's many more well-suited talks on that topic at this conference and many others. What this talk is rather is that we've been trying to educate ourselves on how many of these different parts of the ecosystem sort of fit in together. And this is us trying to share that picture with you. So that said, welcome to CafeGPT. CafeGPT is probably the best cafe at KubeCon 2025. There's this thing called AI that you might have heard of, a couple million times in the keynotes. We have a new customer with a drink request, an iced latte with oat milk. We have a manager and a barista to help fulfill that request to make sure that all of our attendees are sufficiently caffeinated. The manager directs the request to the barista. The barista has access to coffee machines to help fulfill that said request. Each coffee machine has many moving parts. It has the grinder, the steamer, the pressure valve, and so on. The barista uses a coffee machine to make the drink and finally serves the drink back to the customer via the manager. Our customer loves the coffee and, more importantly, loves CafeGPT because the coffee was served in a timely manner and it wasn't very expensive to begin with. So, with that out of the way, let's draw some analogies here. Let's make things a little more concrete. What does serving in CafeGPT look like? The drink request, is the request. The manager is what we are going to call the router that is responsible for delegating requests to appropriate baristas. The barista, to draw a fat analogy, is the LLM inference engine, using resources available to it and then converting requests to coffee. The coffee machines are our GPUs that actually brew the responses. Let's continue making things a little more concrete. What does the lifecycle of an LLM request actually look like?
Yeah, so with those analogies in mind, let's talk about a customer who's trying to figure out something really important. They would like to know how they pronounce kube control. And so the LLM inferencing engine, in our case, is going to convert this user input into an output by using trained LLM models on specialized hardware. In this case, our model doesn't output the final answer because it does not want to be divisive at this conference. But internally, the way LLMs do this is by splitting up our input sequence into small chunks called tokens and running those through the multiple layers of our large language model. As it's doing this, there's a lot of internal representation that gets created as these tokens pass through our model. These can be termed as internal states for now. Using these internal states, the model is able to produce the next token as the output. You might have heard that LLMs are autoregressive, and what this means is that this next token is fed back in, you generate all the hidden states one more time, and you generate the next token. You do this again and again until you hit a special token called the end of sequence, which is where you stop outputting more tokens. As you might have observed, every single time all the sequence prefix that we have calculated so far is repeated on every iteration. This is redundant computation, and it increases latency. So how can we do this better? Well, the answer, as is the answer to most computer science problems, is through caching. In this case, we have this special cache called the KV cache. KV is effectively the key value pair, which is one of the hidden states in our model. So the forward pass, the process of generating the output, using KV cache looks like, first, processing the entire input sequence. You generate all the hidden states, and you store those in this KV cache, which is effectively just memory on your GPU. Once that is done, you can forget about your input sequence. And now you just use all the KV cache representations to generate just one new hidden state, and you use that to generate the next token. You repeat this, so you push this generated hidden state back into the KV cache, and just keep repeating this process until you hit the end of sequence. KV caching speeds up LLM inferencing by up to 5 times, but it comes at an overhead of higher memory use, which can become a bottleneck for concurrent processing. To help visualize this, if you have an 8 billion parameter model and you're trying to serve it using floating point 16 bits, it's going to occupy 16 gigabytes of memory on a 40 gigabyte memory GPU. That only leaves about 24 gigabytes of memory for your KV cache. And if you're using a model with 8K context length, this specific model, every single KV cache can take up a maximum of 1 gigabytes for each request, which limits your concurrent requests to about 24 per second. It will actually be even more, slightly lower due to overheads. And so, as a result, a lot of research has emerged to make better use of this bottleneck. I've linked some papers below, which you can check out from the slides, which I'll upload after this talk. So with KV caching in place, we now have 2 separate phases in our serving process at CafeGPT. The first phase is called prefill. This is where you do all the prep work, you grind your coffee beans, and you gather all the ingredients that you need. Next, once this is done once for your request, you can start your decode process, which is multiple iterations of small units of work where you're just waiting for drops of coffee to come out. We'll keep coming back to this analogy to make things clearer. But with this in mind, I want to call out a few important characteristics of our LLM inferencing workload. The first one is that prefill is computationally intensive. It takes effort to grind that coffee, but it lasts a short duration over your entire request lifecycle. Decode, on the other hand, is not computationally intensive. You're mostly just waiting for drops of coffee to come out. It's called memory bound instead because the KV cache reading and writing tends to be the bottleneck here. But it lasts a long duration of your entire request, especially if you're outputting a lot of tokens. And importantly, you also don't know when the decode is going to end. This is kind of different than traditional web app requests. You kind of just wait for the end of sequence to be output out, which is when you realize that, okay, this request is finished. From a customer's point of view, there's a few SLAs that we need to adhere to. The first one is a low time to coffee, which is analogous to request latency. We also want a low time between drops, which is especially important if it's an interactive application like chat. And importantly, the customer might want a low time to first drop, which is the first token that they get. From a provider's point of view, we want to serve a high number of coffees per second, which is our throughput metric. And since we want to serve these at a low cost, we want high machine utilization because we want to extract the most out of the machines that we have. And importantly, a lot of different customers might have different SLAs. Maybe you're someone who's in this image who really wants their coffee now, or you can just wait for it. You're not urgent, and it can be a batch processing job. So to work on these SLAs, let's see how you might attempt to serve this. Let's first meet our novice barista. They're new at the job, and they can only do one thing at a time. When they get a request in, they first do the prep work, the prefill, output the first token in this image, and then they process the decode tokens one by one. Our novice barista is not able to do multiple things together, and this results in a problem because if there are more requests that come in, they can't do any work on them until the entire first request is finished. And again, due to our workload, this is a problem because we don't know when that is going to happen. A more experienced barista can batch things together. So the way this looks like is when you have only one request, sure, you start with the prep work for that. But when another request comes in, as you're waiting for a drop of coffee of the first request to come out, you can start to prepare you can start to prefill other requests. And this is kind of where GPUs tie into the picture. GPUs are great for batch processing multiple tasks together, and we can make use of this. So in this batch, we are doing prefill of the second request and decode of the first one together. And you can continue to do this. For the third request, you can batch 2 decodes with 1 prefill. And ultimately, you just wait for all the coffee to come out of your machine. This has immediate gains. The first one is that your throughput can increase by over 10 times due to batching because you're doing more concurrent processing for each request per second. And your request latency also improves because you're not waiting for requests to queue up. You can start making progress on them earlier. However, one problem that you might run into is that your batch sizes are now dynamic. What I mean by this is that every single iteration can fluctuate up or down depending on how much work you're attempting to do there. If you're just waiting for a coffee drop, it might take smaller amount of time, but if you're also batching that with grinding coffee beans for 2-3 requests, that entire batch will take longer to finish. This is called interference between prefill and decode and can result in fluctuating latencies of your time to first token or your inter-token latency. And effectively, your batch size, which is the amount of work that you're doing, is what is controlling this latency. So if this is a problem for you, if you really want to serve consistent SLAs of latency, what you might prefer instead is prefill decode disaggregation, which you might have heard of in other talks in this conference. The key idea there is pretty simple. If these are conflicting workloads, you just separate them out onto 2 separate devices. You do prefill on only one machine, and you do decode on a separate machine. So on the LLM inferencing engine on the left here is responsible for doing prefill. And once it has computed the entire KV cache, it just transfers it over to the second decode. Not only does this prevent interference between 2 different prefill and decode pairs, it can also help you optimize your machines better. So as we talked about, prefill tends to be computationally intensive, so you can get computationally heavy GPUs that are optimized for heavy compute and reserve those for your prefill instances. Decodes don't require that much horsepower, so you can just give it a lighter machine instead. So that's all pretty cool and all, and I hope you've set up some of the context of LLM inferencing. How do we deploy and actually run this in production?
So can we use existing infra? Can we use the same infra but then run a newer workload on top of it? I think it's a fair statement to make that Kubernetes has sort of become the de facto platform for most infrastructure platforms in companies, or the infrastructure layer for these companies. And this picture on the right over here is from KubeCon Paris in 2024, where one of the core maintainers of Kubernetes said inference is sort of the new web app. And this is kind of interesting because Kubernetes initially was made for web apps and to scale web apps, and then over time it sort of evolved its core to support newer workloads. And inference is just yet another newer type of workload. So it's an interesting new workload with unique characteristics that we just learned about. And it can be served reasonably well without having to reinvent much of the wheel. But to get to this point, there's been substantial efforts that have been ongoing for the last couple of years in order to better support these sort of workloads. And as I said, the community has been relentlessly evolving the core and ecosystem projects as well to better support this sort of workload. Now, when I say this, what exactly do I mean? What do these efforts look like, right? So let's start building bottom up over here. Let's say that you want to host the model and serve some requests, right? Let's start very simple. Maybe your model is small enough, or in what we like to call espresso models, they fit into a single GPU. So you have one GPU, you have an inference engine on top of that, and that holds your model in its entirety. A request comes in, it gets routed to that inference engine or that pod in Kubernetes, and the request is then served. You can request for a GPU on that pod by using something like, by specifying resource limits by nvidia.com/GPU:1. This is good enough if you need one single GPU. It may also be the case that you may not even need an entire GPU. Maybe all you need is a fraction of a GPU for your workload. You can also request for just a fraction of the GPU using MIG partition devices. So MIG stands for multi-instance GPUs. There are excellent KubeCon talks on this in this KubeCon and the previous KubeCon as well. However, as a vendor, you may need to statically pre-partition your devices. So you may have to say that my one GPU, let's say, has, I partition into 2 halves or 4 1/4s or 1 1/4 and then a subsequent number of 1/8s, right? So you may need to pre-partition your GPUs in order to better serve these workloads and then expose these partitions as individual devices. This may not, however, be very resource efficient because if I need 1/8 of an H100 GPU, I might be forced to run on a slice that's larger than what I need if the way I've pre-partitioned it does not match my actual workload as of today. So this leads to resource wastage and then, of course, leads to wasted cost. The second sort of interesting caveat in this form of scheduling and resource management is that you may not really care about what type of GPU you want. All you may care about is, I want 20 gigs of GPU memory. And you may not worry about where that memory is coming from. However, if you sort of stick to the default or the older way of doing resource requests, you may end up with stringent requirements that I only want an A100 or I only want an H100, but you may not have those available. However, you may have other GPUs available that can actually serve those pods, and you now have wasted capacity. You may have already heard about this effort called dynamic resource allocation quite a bit. So DRA can help with that, as you may already know. So for example, now this is an enhancement that's currently being worked on. So this is fresh off the press. So in case you're interested, you should definitely check that out. It's very, very interesting to read through. There's a lot of really good technical details in there as well. But what this allows you to do is it allows vendors or it allows device providers to partition GPUs on the fly. So device drivers can now implement logic that can partition GPUs on the fly. So you don't really need to statically do it beforehand. As long as the request is partitionable, so there are some criteria as to when you can partition it and when you can't. But if it is, you can do it on the fly, leading to like more, you can pack more resource efficiency into that one node essentially. The second thing that it also allows you to do is flexible resource scheduling, right? So you can express things like, can you please give me a GPU which has at least 10 gigs of memory? So having this flexible model of resource scheduling is extremely helpful, especially in cases where you need to auto-scale, which we will soon talk about. So now that we've made sure we're getting the most bang for our buck, how do we actually scale this out?
So since we want our cafe to be able to handle many different kinds of scenarios, there might be certain problems that we run into if you're only serving a single instance. We might have surges in the morning and at lunch, and slowdowns at night. We can also have surges of specific kind of drink requests on certain occasions. For example, an increased number of pumpkin spice lattes during October. We might also be serving different kinds of workloads. Maybe some days we have a lot of espresso requests exclusively. For LLM serving, these changes manifest as conversation-heavy versus coding-heavy tasks, which have different workload characteristics. Or also an increased number of requests for certain models. Maybe the recent GPT OSS came out. To respond to these challenges, we can make use of horizontal pod auto-scaling in Kubernetes. But what do we scale on? CPU or memory utilization is clearly not a good metric for us here because that's not the main bottleneck at all. We're using GPU and GPU memory here. You might try to then use maybe concurrent number of requests, like the queries per second. But that is also not a great metric for LLMs because different requests are created unequally. A summarization request might take in a lot of input, but only output a small summary. Code generation, on the other hand, might have a simple prompt that's outputting entire files of code. Traditional auto-scaling metrics, as a result, are not a great fit for LLM workloads. So let's take a look at what works instead. Queue length, as it turns out, is a really good metric of your load. An increasing queue length indicates that our barista is not being able to keep up with their orders. Any new requests are going to face blocking until all pending requests are completed, which is unknown to us. As a result, auto-scaling on queue lengths can help boost your processing throughput because the new machine can start to take up some of that load. And this can reduce queuing delays in the process as well. However, I'd like to call out that adding a new machine does not lower latency of your processing requests that are already in flight on another machine. You can understand this as if you add a new coffee machine, your speed of the first one is not going to go up. So you can't increase your inter-token latency, for example. If that is indeed a concern for you and you want to auto-scale on those violations, you might instead consider taking a look at your batch size. As we talked about in an earlier slide, the size of your batch is what is controlling how long it takes for you to output a token. And so what you can do instead is configure your serving engine to keep batch sizes low and monitor the number of batched tokens that you're running with. In this way, by scaling on your effective batch size, you can scale earlier than queue buildup and still continue to meet your SLAs. One thing to keep in mind with this is that you might overreact to temporary spikes, but maybe that's okay for you. I also want to mention that since we earlier talked about how prefill decode disaggregation is what is allowing you to meet your latency goals, you might also consider scaling up your disaggregated prefill deployments. So if you're running with one prefill and 2 decode instances and you want to scale them up, you have 2 options. First, you could scale up your instances while keeping this ratio constant. So you could add 3 more instances, 1 prefill and 2 decode. This can be great if you have a lot of GPUs to spare, and also if your workload has remained the same, but you're just seeing a lot of surge in traffic. An alternative solution that is available to you is to instead just scale up individual prefill or decode instances. So in this case, if you have more summarization tasks, which are prefill heavy, you can just add a new single prefill instance. This is also useful if your workload is starting to shift more, like maybe it's going from prefill heavy to decode heavy, which can happen from conversation to coding workloads. Finally, since we talked about how KV cache can tend to become a bottleneck, a very important metric to target here, to auto-scale on, can also be how much KV cache space you're using up. You have 2 approaches here as well. The first one is reactive. You can monitor and scale if your KV cache utilization is exceeding a certain threshold. For example, if you're consistently running more than 90% at your GPU's capacity. Your alternative solution is to profile your workload and using the calculations that we did earlier, so estimating how much KV cache you need to serve every request, you can see how much you need to run at a particular queries per second. And you can use that measurement to scale up your nodes because you can estimate how much GPU memory each additional pod is giving you.
So now that we've had some auto scaling in place, we've added some more replicas onto our nodes. The one thing that we need to start thinking about now is how do we load balance across these replicas, right? Can we do better than round robin? I think we should do better than round robin. The sole reason being that sending requests might, in a round robin fashion, especially for this workload, might result in extremely degraded performance. And the reason for that is you may end up with hotspots on certain instances solely because of the fact that you don't really know what each workload is going to constitute. You don't know if it's a prefill heavy workload, you don't know if it's a decode heavy workload, and then the interference might actually degrade the performance quite a bit in this case. So your inference engine, as you recall, is already caching process tokens, which is what we've termed as the KV cache so far, right? The router can actually take this information to better balance requests. So one way to actually route requests is to actually route them by being aware of KV cache presence on all of these replicas. So if a single node, if you're doing a multi-turn chat application, you may want to direct all of those requests to a single replica because that has all of those tokens cached, and it's significantly better for your latency. And the Kubernetes Gateway API Inference project actually supports this as of today, right? So it supports all of these routing models as of today, and it's pretty mature. It's getting there at least. So you should, if you're interested, you should check that out. And also, if you're interested in contributing, I think that they could use the help as well. So check that out. That said, you also don't want to route to the same instance all the time because you might end up overloading it. So you might want to build an escape hatch in there somewhere. But in what way do you build that escape hatch? We can route to the least loaded replica. And the way you calculate least loaded can be a couple of ways, right? One of the common ways is KV cache utilization that we spoke about. So you route to the replica that has the least utilization of KV caches. The second one is based on queue lengths. And the third one can be some custom metric that matters to you and your application. Existing projects such as LLMD and AI Bricks already support such routing strategies and also the ability to plug in custom metrics for routing to least loaded replicas. And that's through the API Inference Gateway project. So these are very interesting sort of complementary projects that are ongoing right now. And they could also use help and contribution. So feel free to jump on those calls, jump on that project and help out. Okay, that's a lot of info. So let's zoom out and look at the picture that we've been building. We have a couple of nodes which have a few GPUs on them. These GPUs may have pods that are scheduled on them, and these pods may be inference engines. The kube scheduler handles that. Now, DRA is the flexible resource allocation and increased utilization part of Kubernetes that provides the scheduling and resource management in a flexible manner that we spoke about. You also have a request that we spoke about initially, which is how do I pronounce kubectl. The API Inference Gateway helps route these requests in a slightly more intelligent manner, as opposed to doing it round robin or some other naive way. And then you have ecosystem projects like LLMD and AI Bricks that provide such routing and many other such capabilities, like auto-scaling as well. So our question was, how do I pronounce kubectl? So what is the answer, right? So we decided to ask the latest ChatGPT model, and it said what it said, right? It said what it said. We're not going to say anything more on that. Maybe this is the right way. I don't know. We hope we've convinced you that you do not need to be proficient in language modeling, and that when you try and work with these systems, you can ground yourself in the fact that serving LLMs is genuinely as tractable as serving coffee is. Thank you for visiting CafeGPT, and feedbacks and tips welcome.